a non-Euclidean universe. What's a Euclidean one? Well, it's just a world in which Euclid's axioms hold. That is, Euclid's ground rules for geometry. Now, in this program, we're going to investigate Euclid's axioms for plane geometry, and we're going to use them to illustrate the logic behind axiom systems in general. Colin.
Well, actually, we're going to use a modern formulation of Euclid's axioms. In this formulation, there are 15 axioms arranged in 5 groups. But we're not going to go through all of them, just a few to give you an idea of how they go. The first group is the instance axioms. First one says, if I'm given 2 points, then there's a unique line that passes through them. Instant with them is the technical term. Second one says, if I'm given a line, then there are at least 2 points on it. And the third one says, there are at least 3 points that don't all lie on a line. Well, you're probably thinking, why bother to write down axioms when they're as obvious as this? Well, the whole point is, we want to make our reasoning about points, lines, triangles, and so on, completely independent of any reference to the real world, other than those axioms. We want to write down at the start everything that we need to know about the real world, and then we argue just using these axioms alone. That way, we can be sure that we've really proved our theorems, and not just deduced them from a badly drawn diagram, for example. Well, those are the instance axioms. Next come the betweenness axioms, numbers 4 to 7. Here's a typical one, number 6. What it says is, if I've got 3 points on a line, then there's only one of them that's between the other 2. For instance, a line doesn't behave like this ellipse here, where it'd be very difficult to say which of those points is between which others. Congruence axioms are about lengths and angles. This one says, if I've got 2 triangles, and I've got 2 pairs of sides equal, and if the included angle is also equal, then the triangles are congruent. That's to say, they're equal in all respects. Well, that's just a formalization of the fact that I can imagine picking that triangle up and putting it down on top of that one, and they'd fit exactly. The completeness axiom is the familiar nesting property of the real line that you've already met. If I have a nest of intervals that look as though they're converging to a point, then there really is a point there. And finally, there's the parallel axiom, and that's the one we're going to be most interested in. What it says is, if I've got a line and a point not on it, then there is a line passing through that point that doesn't meet the first line, and it's a unique line. That line's called the parallel to this line. Well, the trouble with Euclid's axioms came with that parallel axiom. You see, for hundreds of years, mathematicians felt uncomfortable about it because in order to check whether 2 lines meet or not, whether they're parallel, you have to extend them indefinitely far. And that's something that's impossible to do from the point of view of working on a piece of paper or a stretch of sand. Mathematicians felt that all the other axioms were intuitively obvious. They ought to be able to prove the parallel axiom using the others. Well, maybe you think the parallel axiom is just as obvious as the others, and that mathematicians were silly to try and prove it. But let's think for a moment how you might try to prove it by constructing the parallel line. Given a line and a point, consider the distance between them given by a line segment at right angles. Now, take a right angle from this to give you the parallel line. It's parallel because it stays the same distance from the first line, and so never meets it. But can you be sure that the distance doesn't change? You can't go on checking it forever, so can you be sure?
Well, you might say we've been cheating as usual because this is the equator, and these are lines of longitude, and they're circles, not straight lines. But, you know, for a long time, people believed that they lived on a flat Earth. And if they had taken 2 lines perpendicular to the equator and extended them, then they'd have been very surprised to find them meeting at the pole. Or perhaps if they'd have been very smart, they could have deduced that they were living on a curved Earth. Now, how do we know that our universe isn't curved something like the Earth, so that if we take a straight line and 2 lines perpendicular to it, then they might curve imperceptibly towards each other or away from each other. Well, that sounds a bit far-fetched, but I hope by the end of the program you'll see that it's not really such a harebrained idea.
Well, harebrained or not, I think you can see why mathematicians weren't convinced enough about parallelism to take it as an axiom, why they tried so hard to show that it followed from the other axioms. In this program, we're going to prove that it doesn't follow from the other axioms. And the way we're going to prove it is going to have you wondering, just as Alan promised, whether there really are unique parallels in the real world after all. So let's get on with that proof. I want to explain the method of proof by taking a subset of these axioms to make it simpler. I'm going to take the three instance axioms and that troublesome parallel axiom, and I'm going to prove that the parallel axiom is independent of the three instance axioms. Well, as a matter of fact, it's necessary to talk about consistency of an axiom system before I talk about independence. Why should we do that? Well, consistency just says that the axiom system makes sense, that the axioms don't contradict one another. And it would be fairly stupid to talk about independence of one axiom from another if the whole system doesn't make sense in the first place. In order to prove consistency, I need a model of the system that satisfies all the axioms. And I have such a model here. Each of these balls is a point, and each of these rods is a line in this model. So there are just 4 points and 6 lines. There aren't any others. For instance, on this line, there's just these 2 points and no others. Well, what would the instance axioms say for this model? Given any 2 points, there's a unique line joining them. Well, given these 2 points, there's a unique line joining them, and clearly that's true for any other pair of points as well. Given any line, there are at least 2 points on it, so that's the second instance axiom. And clearly, there are at least 3 points, not all lying on the same line. So all the instance axioms are true. What about the parallel axiom? It doesn't look as though any pair of lines is parallel in this model. But remember, the definition of parallel is just 2 lines that don't meet. They don't have to look parallel, they just don't have to meet. So let's take this line and this point and ask whether there's a line through this point not meeting that one. Well, there is. There's this one down the back. And it's the only one, so it's unique. And the same thing's true for any line and any point not on it. So this model satisfies all 4 axioms. So they must be consistent, otherwise we wouldn't have been able to find a perfectly sensible model satisfying all 4 of them. Well, let's talk about independence now. In order to prove that the parallel axiom is independent of the other 3, I need a model that satisfies the first 3, but not the last. And this simpler model does just that. This time, there are just 3 points and 3 lines. Every pair of points lies on a unique line, and every line has 2 points on it, so that's the first 2 instance axioms, and clearly there are 3 points, not all lying on the same line. So all the instance axioms are true. But what about the parallel axiom? Well, every pair of lines meets, so there aren't any parallels in this model. So this is a model that satisfies the instance axioms, but not the parallel axiom. So you couldn't possibly prove the parallel axiom from the instance axioms, because otherwise we wouldn't have been able to find a model having just the instance axioms and not the parallel axiom. And you can't disprove the parallel axiom either, because here's a model that satisfies all 4. So the parallel axiom is independent of the 3 instance axioms. You can neither prove it nor disprove it. And that's the way you prove consistency and independence. You find one model that satisfies all the axioms, and another model that satisfies all the axioms except the one you think is independent.
So now we've seen the method on a subset of the axioms, let's do it for real, for the whole set of 15 Euclidean axioms. First of all, to prove consistency, we need a model which satisfies all the 15 Euclidean axioms, and that's easy. It's just the Cartesian plane. And by that I mean the Cartesian plane treated algebraically. So, for example, a point is just a pair of real numbers, and a line is simply a linear equation. And all the axioms can be established by simple algebra. For example, through these 2 points, there is precisely one line, because I can solve to find an essentially unique linear equation which satisfies these coordinates. And all the other axioms can be established in just the same algebraic way, including the parallel axiom. For example, given this line and this point outside the line, then I can solve to find a unique line through that point which doesn't meet the given line. And so I've shown that the 15 Euclidean axioms are consistent because the Cartesian plane is consistent, insofar as my algebraic manipulation is consistent. Now, what about the independence of the parallel axiom? To prove that, we need, as before, a second model satisfying all the Euclidean axioms except the parallel axiom. Now, in fact, we have such a model. It's a rather funny sort of universe, which we've constructed in the studio. And here it is. It's just a circular disk, the surface of the disk, but I've constructed it with some rather peculiar properties. Colin. Well, to show you what these peculiarities are, I'm actually going to transport Colin into this universe. Well, it's a small world, but there's more to it than meets the eye.
Well, it doesn't look small to me. It looks as though I can walk as far as I like.
He's getting smaller. Smaller and smaller as he moves away from the center. In fact, everything in the universe contracts as it moves away from the center. That's the way I've constructed the geometry. The width of the bands tells you how much it contracts. Of course, Colin doesn't see the bands decreasing because he gets smaller in proportion. This is Colin's view of his universe, and the bands look equal in width to him. So he can't even tell that he's got smaller because everything has got smaller in proportion. In fact, if Colin were to walk to the edge of his universe, he'd disappear entirely. That's how I've arranged the rate of contraction. Well, that would be too sad, so in fact, I've arranged he can never do it. You see, as he gets nearer the edge, his steps become so small that he'd need an infinite number of them, so he can't reach it. Well, this is going to be the model for our Euclidean axioms. So what do we need? We need points and lines. Well, here in fact are a couple of points. Now, what about a line between them? And this is where the model really becomes interesting.
Well, it's quite obvious to me what the straight line is. It'll trace out the shortest path, and I can measure that. There we are, 4 units.
So what seems like a straight line to Colin is actually a curve for us. That's very interesting. This is what I would have thought a straight line ought to look like.
Well, I don't know what Alan's talking about. He's put down a curved line. It's quite clear to me that that's not the shortest distance between the 2 points. Anyway, I can prove it by measuring it. I'll use the same units as I did last time. There we are. 5 units instead of 4.
Now we can see why lines look different for Colin. You see, when he measured along this line, which he saw as curved, his rulers were further away from the center, so they were smaller, and he needed more of them than when he measured along this path. The rulers then were nearer the center, bigger, and so this was the curve of shortest distance. In fact, Colin would even see this as being straight because even light would bend in his universe to take the shortest path. But let me be a bit more precise about these curves of shortest distance. Of course, the curvature depends on the contraction that we've chosen. And I've chosen the contraction in such a way as to make these curves very special ones. In fact, I've chosen the rate of contraction to be such that if we extend the arc between the 2 points, we get a circle, cutting the edge at right angles. In other words, I've constructed this model universe so that the definition of a line through 2 points is in fact the arc of the circle through the points, cutting the edge at right angles. In fact, this satisfies the first Euclidean axiom, which states there's a unique line through 2 points. You see, there is only one circle through 2 points cutting the disk at right angles, so Collins' line is unique. Of course, for Collin, this actually looks like a straight line. In fact, it looks like an infinite straight line because he can never reach the edge. Well, that's one of Collins' lines. In fact, every line is like this. Every one of Collins' lines is an arc cutting the disk at right angles. There is one case when Collins' lines are not curved. A line through the center is a straight line, even to us. You could think of it as part of an infinitely large circle. So that's what points and lines look like. What about triangles? Triangles have curved sides, of course, unless a side goes through the center. Let's just see what happens when we move the triangle towards the edge. It'll get smaller, of course, but look closely at what else happens. As well as getting smaller, the sides get more curved. Let's just see that again. So the geometry of Collins' world is just a wee bit peculiar, but we've got points and lines and triangles, so we can check the Euclidean axioms. We must remember the definition of a Collins line. It's an arc of a circle cutting the edge at right angles. And with that definition, we've already verified one axiom. There's a unique line through each pair of points. Well, now that we've got a triangle, let's verify a congruence axiom. If you've got two triangles and two sides and the included angle are equal, then we want to confirm that the triangles are congruent. In particular, that the third sides are equal. Well, here are a couple of triangles with this side equal to this side. The white sides are equal and the included angles are equal. Well, the sides don't look equal, but don't forget length contracts towards the edge, and the third black sides don't look equal either, but that may be for the same reason. Anyway, for Collin, this is just a pair of straight edge triangles, so they may be more obviously congruent for him.
Well, I can easily check if they're congruent. All I have to do is take it over and see whether it fits exactly onto the other triangle. Well, before I put it down, I think I can prove that it's going to fit just from the fact that lines are unique. You see, this side is going to fit exactly along that side, and then this angle's the same as that angle, so the white sides are going to fit, and because they're the same length, the back corners are going to fit as well. And so the back lines have got to fit as well, because lines are unique. Well, indeed, it does fit. And so you see, congruence just follows from the fact that I can move triangles about. It's very easy.
Well, that simple moving about was from Collins' point of view. Now, here's approximately what it looked like to me from my outside point of view. So even from our point of view, the two triangles fit together if they're in the same location. Anyway, that makes two Euclidean axioms that we've verified, Axiom 1 and Axiom 13. Now, what about the parallel axiom? Given a line and a point not on the line, that states there's a unique line through the point not meeting it.
Well, why don't I try and check that axiom using the black line, the edge of the triangle, and that point? Well, it looks to me as though a line somewhere along there wouldn't meet the black line, but how would I be able to check? I'd have to extend the lines indefinitely far to see whether they meet or not.
So Colin isn't able to check the parallel axiom because his universe is infinite for him. But we can, because we can see all of his universe. Let's take Colin's line extended. And let's try to find a parallel line through the point. Well, this was probably the line Colin had in mind. Remember, all Colin's lines are arcs of circles which cut the disk at right angles. Now, this line doesn't meet the black line in Colin's universe, so it's parallel to the black line because that's the definition of parallel, two lines which don't meet. But here's another line through the point which doesn't meet the black line, a second parallel line. And here's a third one. So you don't get a unique parallel in Colin's universe, and that's just what we need to prove independence of the parallel axiom. Because remember how proof of independence goes. You take your axioms, and then you look for two models. One in which all the axioms hold, and that proves consistency. Now, remember, that was just the Cartesian plane. And a second model in which all the axioms hold except the parallel axiom. And that's just Colin's universe. Well, we only established a couple of axioms in there, but believe me, they all hold. All of them except the parallel axiom. Through this point, there are in fact an infinite number of parallels, lines, which don't meet this given black line. And so that finally proves that the Euclidean parallel axiom is independent of the others. Well, that about brings us to the end of the program, but there's one intriguing fact about Colin's universe that we might be able to illustrate. You see, as far as Colin is concerned, everything in there is quite normal. All the Euclidean axioms seem to be obeyed, just as in the Cartesian plane, except the parallel axiom, and even he can't tell that that's not obeyed. But perhaps there is something that he might be able to check to show that he's in a strange universe, and that concerns the angles of a triangle. If we take a triangle in Colin's universe, and if we draw the corresponding Euclidean triangle, then we can see that Colin's three angles are smaller than the angles of the Euclidean triangle. So they must add up to less than 180 degrees. In fact, the bigger the triangle, the smaller the angles. So for larger triangles, the discrepancy from 180 is even greater. Now, the question is, can Colin detect the discrepancy? Well, it so happens that when Colin measures an angle, he gets exactly the same number as I do. At least that's something we can agree upon.
Well, let's see what this angle is. And this one. Well, they add up to 150 degrees. So I can tell there's something peculiar about this universe.
Well, what about the world we live in? We know that if we take the sum of angles of a triangle, we get 180 degrees. Or do we know? Supposing our world was just a large-scale version of Colin's universe. Then, for the sort of triangles that we measured every day, we might notice the discrepancy. But if we took a really huge triangle, where the discrepancy was much greater, then perhaps we might be able to detect it. So, how do we know that we don't just live in a large-scale version of Colin's universe? Well, we don't know.